Hello, good evening all. So we will be waiting for 2 minutes. Let others join and then we will start. Okay, so good evening all. So let's start week two's open session. So I will be sharing the screen and most probably we will go through the concepts. So as and when we go through, we would do some explanation, some discussion. And in the meantime, if you have some doubt corresponding to those concepts, right, you all can ask those things. Yeah, some little new things also we are planning to discuss regarding the concepts already taught by professor, right? Is my screen visible? No, ma'am.
No, sir.
Just a second.
Yeah, it's visible now.
Yes, sir, it is visible now.
So what can you see now?
Yes, sir.
No, I mean
Contents of week 2, PDSA week 2.
PDSA week 2, right? Okay, fine. So You all can see the text, right? Complexity, the complexity of an algorithm is a function, right?
Yes, sir.
Yes, sir.
Okay, fine. So let's start it, and just tell me one more thing. Can you all see this? Can you all see a white screen now?
Yeah.
Okay, fine. Great. So can someone just tell me what do you understand by complexity, and not the definition, but what do you mean by time complexity? There is another complexity which is the space complexity, and that is not discussed by sir, and we are not actually going to discuss that in very detailed way. A little bit of that we would discuss, and as and when we proceed, some space complexity features would come up, obviously, right? So, but what do you understand of time complexity of an algorithm?
The time taken to execute a particular program running on an algorithm.
Sorry, can you repeat? Your voice is a little bit hazy.
It is the time that a computer takes to execute a program running an algorithm.
Okay. So we know a concept of asymptotic time complexity, right? We learned those things in this week. So why do we need to consider asymptotic time complexity? I mean, I can just run a program on my computer and see the time, how much it took to measure the efficiency of that program. Why are we going into this complex notion of order of n square, big O of n, right? These things, big O, these symbols, right? You all know. So why are we going into these complex things?
So that we can compare the different solutions that we have come across and choose the better one, the more efficient one.
So that can also be done by simply running different solutions on your machine, right? You can compare the timing. Suppose your first approach took 1 second, second approach took 1.2 seconds. So then
There may be
Same.
times when the
Sir, maybe
input is
because
very
of the
large.
size of the data.
size of the data, yeah. But how will you relate that? I mean, can you just rephrase what you are saying, or maybe elaborate a little bit?
Sir, as the input size goes on increasing,
Okay.
so at that time it is very difficult to it is difficult to do as you said, it's very difficult to calculate.
Okay, fine. So you're saying that let's make input size as a variable in the function, or maybe let's make the time as a function of the input size, correct?
Yeah. Yes, sir.
Okay, fine. But that is okay, that we will do that. Good. So we take that point. So let's make the time taken by a program as a function of a variable. That variable is actually the input size that that program is accepting. Fine.
Yes,
That is
sir.
also logical, because yeah, every program would run depending upon it would take time depending upon the input size, correct?
Yes.
Fine. So that is one very important point that we consider. Second thing is, which is particularly to the concept of asymptotic notations. Why do we need to go for asymptotic notation? So what I mean is, let's say wait, fine, let's say we our program 1 p1, right? P1 takes n is the input size, huh? Just consider n is my input size. Fine. So my p1 program, for the same thing that I want to achieve, the both program p1 and p2 will do the same thing by two different approaches. So p1, let's say, takes 3. You calculated the time, right? You calculated the time, and let's say the time came for a list of 100 length, for a list whose length is 100. You check the time was something around, say, 200 millisecond. Fine. So you can say that if my list takes a list of 100 size took 200 millisecond by program 1, so I can say that my program 1 is directly proportional to the 200, right? 200 is the total time and 100 is my list size. So if I do 200 by 100, that is 2. So 2 is the constant factor which is getting generated over here. So I would say that it is something around linear time. I mean, I would write something, right, 2n to generalize it. Right, my P1 would take 2n time. So this is the unit that I'm using, 2n. And let's say accordingly all conditions remain same. Let's say it took 300 time. And accordingly everything same. What you would get here is 3. And I would say my program 2 took 3n time. That also can be done, right? So this is slower and this is faster. So I got it. P1 is faster. Problem solved. Use P1 approach. But why you got it, right? So 2n is obviously smaller, 3n is larger, so 2n is lesser time. So and it is also expressed as a function of the input size. That is also achieved. So why do we need to go for asymptotic notation? That is your order of an omega and your theta.
Sir, in mathematical term, it is an approximate, right? Omega, big O.
Yeah, fine.
I
So
think
that's why we use
See,
that.
the answer
Yes.
is something very much practical. You may not have to go into mathematical proof to say, I got your point. These are approximation, but we will come to that later. First of all, why do we need to have a system or a metric to mark the time complexities in these forms? There is some practical significance for that, right? So what is that? That I want to actually ask. Yeah, someone was saying, can you continue?
No, I was just saying, like, when I say, or when we say asymptotic, it means basically like directly we cannot figure out like which one is greater or lesser, right?
Yeah.
So indirectly we are trying to figure out like if we have to compare two things and directly we cannot compare, so there should be some other way to compare them. So that's why like these notations are there. I mean, this is what I understood by the word asymptotic. Yeah.
Asymptotic. Yeah.
Yeah.
So asymptotes are something which is a thing which comes in mathematics, but we would not go into that. And but yeah, obviously, if we have that intuition, it would be much more clear. But that's not required. First of all, see, one feature of asymptotic notation is that those of you who have gone through the concept of this week, you would know that we do not consider constants. We remove the constant. So apparently, both of these are same in efficiency, same efficiency. Right, same efficiency. I would say both P1 and P2 program are of same equal efficiency. None of them is better than the other according to asymptotic notation. So why are we going into this system? The main idea is, see, when you are comparing these factors, now what I did, see this approach. I just took the overall time taken by CPU. This is the overall time taken by CPU, right? Overall time by your computer, right? CPU, and then I divided by the input size, right? What happens when you simply run this P1 program on a faster computer whose clock speed is more? In that case, your overall time would reduce, right? Input size would be same. Your overall time by CPU would reduce. This, mind it, this is the overall time in second. So that is unit of time, right? Second or millisecond, whatever. So that would reduce in a faster computer. Now in a faster computer, what happens is this would further reduce. So I cannot guarantee a specific value of timing or any specific unit or metric for the efficiency of a program when I consider it in terms of units of time. Why? Because there can be system dependency and also there can be language dependency. A same algorithm can be coded in C, it would run much faster. When it is coded in Python, it would run much slower. Right? Sir has actually described the whole process. He has given the explanation of with the data, right? So Python would be much slower. So when I write the same algorithm, it would run faster in one system and in another system it would run slower. But that is not a proper standardized way to compare, right? You cannot, because the algorithm concept is the main thing, right? Whether you are running it on a machine in what language, that doesn't matter. Concept is important. So I should judge only on the basis of concept. So in order to eliminate these variations due to system and language dependency, which are essentially comes up as a factor, as a constant factor most of the times, right? In some later cases that is not in our syllabus, we would see that it comes up in some other coefficient values also, but that's okay. Most of the times consider it comes up as factors, as constant values, right? So these constant values which represent the system and language dependency, we would filter all those out, right? And we would only consider the number of iterations done by that algorithm on the input that we are giving. So obviously you are incorporating the input size, and your function is basically, so I would write the complexity as, right, complexity is equal to a function of input size, and this complexity function is nothing but the number of iterations. Okay.
So you mean like this complexity?
Yeah.
So when you say like any program is dependent on two things, one is system and second one is like language.
Yeah.
So don't you think like then in that case we are comparing apple with orange? Reason is very simple, because sometimes or at times program is dependent on system also or language also, right?
Yeah, that's what I'm saying. Language and system dependency. Yeah.
So that doesn't comes under complexity.
No. See, whenever you are deciding a plan, right? You have a real life problem. You have to solve that by using some technique, right? Some the so-called algorithm word. You have to devise some algorithm. So when you are devising some algorithm, you would only think in terms of the mathematical way. You are not going into the in which language if I code it would be faster, in which system if I run it would be faster. That's not an analytical way to compare two algorithms. So I'm giving you an example. You created an idea to solve a problem. Another person created the same idea to solve a problem. Now I should give equal credit to both of you, right? But if you run it in some machine and another guy run in some other machine, if I'm only looking at it from the perspective of just the technique that both of you are using, right, and not the implementation, so then I should give equal credit to both of you, because both of your ideas are same. Only difference is you have used different languages, or maybe you are running it on different machine. That's why the timing is different, right? But I've not asked you to do that. I've asked you to just think of an algorithm, think of the idea, not the implementation. So whenever we are comparing a solution, we have to compare it on the basis of the idea and not the ultimate implementation, right? When you are devising an algorithm, thinking of an algorithm, when it comes to real life software, that is different. But mostly, see, how will you make a real life software? At first, you have to think of an approach to solve it, right? Not if you are doing web development, that is different. But when you are actually tackling a real life problem that has no solution, and you have to think of some way to do that, then how will you do that, right? I hope you are getting the point what I'm saying. So in that case of that kind of scenario, only your technique matters, not the implementation.
No, so what I understood, you were saying like you people, I mean, this complexity is only concerned about the idea, the algorithm, not about the language or not about the system.
In order to eliminate the dependency of language and system, that's why we are using asymptotics.
Right? Because many a times what happens, C++, is little bit faster than Python.
Yeah, that's what I'm saying, right? The same thing I'm saying, that's why it should not be compared. You are writing bubble, let's say selection sort on Python. You are writing the same selection sort on C++ or C. Your time would be much lesser on C++. In Python, it would take more time. So should I give more marks to the guy who wrote in C++? What's the point? So the idea is same, right? Whichever language you use, that's not a matter of, I mean, what should I say it? The algorithmic intelligence, right? So even if you write a pseudocode, then also I should give the equal marks, because that's the idea, right? And that's why in many places, you would see most of our course questions are also on the basis of pseudocode or some theoretical concept. In most of the graded assignment or in the in these kind of questions which are graded, we try as much as to give language independent features, right? So that is the idea. You should not consider language and system dependencies, and in order to eliminate language and system dependencies and to only consider the performance of an algorithm by the core idea that it incorporates, we use asymptotic notations. Fine, we will not go into any timing like 4 seconds, 5 seconds, this algorithm takes 10 seconds. We would not go into timing in terms of units of time. Rather, we would go into timing in terms of functions of input size, which represent the number of iterations. Right? So that would be same. Number of iterations would be same. Only the speed of the iteration would be different depending upon your machine or language. That doesn't matter. Number of iterations would be same if you use a specific algorithm.
And there is limitation of system also. We cannot go beyond it.
You cannot go beyond it. Yeah, exactly. Got it. Yeah. Any doubt? Please clear this concept very nicely, because first doubt that should come to your mind when you think of measuring the performance of any approach, any algorithm, is why I am going into n square, n cube, all those things, when I simply have millisecond, second, and all those time units. Anytime we use measuring any speed, we measure it in terms of time. So why are we going into functions of input size? Yeah, fine.
And what is the significance of O naught or sigma or theta?
Yeah, that I would come. That I would just come after this. At first, just this point. So asymptotic notations, as we said, complexity. So this is actually theta, omega, and O, big O. Now, what are these things? I would come in the next part, just after this. But before this idea, why we are going into this O, sigma, theta, whatever, right? Why are we going into this thing? That should be clear. Is that clear with everyone? Someone has any doubt?
So basically, we are trying to like streamline it without any, like we are trying to set a basis, is it? Like, is it the gist of this? Like you said, it should be independent of the programming language, right?
Exactly.
So we are just trying to like give a standardized version of what.
Exactly. We just want to make a standardized version. So I don't know, but those of all who have learned science in 11-12 class, those of you can relate that we used to learn the SI units, right? And I mean, many others would know this, that SI unit, that standardized units are there for every type of measurement that you have, for time, for speed, for current amount, all those things, right? For distance, we have a standard unit to compare it. So asymptotic complexities are, you can say, it's a standard unit, standard way of comparing different algorithms, which would be system and language independent. That is, it's better to say, which is implementation independent. Fine.
Yes.
I have a small doubt.
Please, yeah.
In the lectures, sir said we're mentioning upper bound. Like there's a lot of calculation that we do, like if it's less than that.
Exactly.
Is there can we say that if it is less than n complexity, like if it's if a certain function is O of n square, it is also O of n cube?
Yeah, we can say that. I would just come to this part, then we will do that. But you can say that.
Okay, sir. Thank you.
Fine.
And one more thing, because all this algorithm depends upon like how clever is your idea, right?
Exactly.
And it's like ongoing process, because of course, like there are certain algorithm which is known and which is very common.
Exactly.
But there are so many things which is not very common, right?
Yeah, everything. I mean, when you come to real life problems and when you come to interview problems, the first thing that every interviewer would ask you is give the basic solution, the naive solution, and then incrementally improve upon it, so as to check how much you can think, right? So it's very important to improve and learn the way how to improve your algorithm. Yeah.
Because in the real life, like you start from the scratch and then you keep on improving.
Exactly. And that's how you should be also following the chapters also, that I would request you. that whenever you see a real, I mean, in the lecture, whenever you are seeing the lecture for the first time, just don't see the solution and don't see the approach that sir is taking, huh? Since it's a lecture, there are time bounding features, like we cannot go beyond a certain time in the lecture. But I would request, when you watch the lecture, just do not see the jump into the solution or the algorithm first. Just understand the problem statement.
What person you're calling is not answering. Please try later.
Right? Sorry, can you mute someone's here? So just try to see the problem statement and try to think of a solution that you can come up with, the easy solution. After that, see how sir is explaining it, right? So you would understand how your solution is a little slower and how this approach is making it faster. So when you see this difference now, you would learn to think how to improve your algorithm, right? Otherwise, learning algorithm, if you just see the approach, that's not going to work in the long run. You should be able to learn how to think to improve your algorithm. Fine.
Sir, I want to ask a thing, sir. Hello, sir.
Yeah.
Sir, how to implement those codes, like those kind of sorting techniques we have learned in this week now. So I want to ask, like, how to implement those codes in our normal life codings. Like when we solve the question, how to implement those things.
The codings are normal, right? I mean, do you want to ask implement, I mean, some real life interpretation? I mean,
no, sir. Like if you are coding something, if you have a question and we want to code on it, so okay, what thinking we should have, we should be implementing this kind of sorting technique or that kind of sorting.
Yeah, that I would discuss. Very nice. Okay.
Yeah, so, the way of implementation, like what kind of thinking we should have.
Exactly. Yeah, I would discuss that. So how to implement, that is quite easy. I mean, I would not say easy. I mean, it's okay, you would learn that. But how to think which sorting to take into place, that I would discuss. So order of that thing, and second is which sorting. Fine.
And one more thing, when you said like you were giving the analogy of SI units, right?
Yeah.
So that is kind of a standardization. So here in case of complexity, because all the algorithms are initially naive algorithms, and with time, like we keep on improving, right?
Yeah.
So how it is standardized? I mean, standardization with respect to what?
No, see, the algorithmic complexity of an algorithm is not what we are planning to standardize. We are planning to standardize the way in which to measure that complexity, right? Like you can say that I would measure in seconds. Someone would say I would measure it in the as a function of input size. Someone else would say I would measure it in the clock speed, right? So that should not happen. There should be something which is independent of systems and languages, and that should properly incorporate the features of your core algorithm. Yes.
So it means like we are saying we are trying to formulate the component of any algorithm, right?
Yeah, you can, correct.
Okay.
So standardization means what? We are setting the metric. We are not defining it as constant. Correct. What you are saying is, if you are making a complexity of an algorithm as constant, that is not what we are trying to do. We are trying to set a metric to measure the complexity of algorithm. We are never saying that you have to every time say that this algorithm should only work within this time. That is not standardization. Standardization is not forcing you to make something constant. Standardization is only asking you to measure something in a specific way, and that should be conventionally followed throughout the world. That's it, right? Okay, so now let's move to, so this is clear, I hope, why we are going into asymptotic notations, right? And 2-3 features of asymptotic notations, sir has also explained that in lecture, right? Number one is the constant thing that I told, that whenever you have something like constant 2 and 3 and 4 and 5 and whatever, even 1 crore n or 10 to the power 2000 n, but we would not consider. So apparently your n by 200 is equal to see, so now these two numbers are hugely different. I mean, if you calculate it mathematically, but if I simply say that these are asymptotic notation, so what is this O and what I would explain that? It's already in the lecture, but still. So then both of them would be nothing but order of n. Fine. So these constants we would tear apart. No constant matters in algorithm. So I hope you all have done logarithms, right?
Yes, sir.
Yes, okay. Yes. Fine. So is this statement correct considering this is algorithmic? I mean I'm talking about O notations, huh?
Yes, sir.
Can you explain why?
So when we compute it in natural logarithms, there is a constant.
Fine.
Which
So
is,
if I consider it in terms of natural logarithm, what will happen? It
there
will be
will be
something like correct. So this is essentially a constant, this value, which is 1 by, right, 1 by log 3 base e, and there is also 1 by log 2 base e. So those constants we would leave out, and it's actually order of log n. This e3, so that's why it's very important, whatever is the base of your logarithmic function, if you are considering big O notation or whatever, I mean as any asymptotic notation, then the base does not matter. Fine, just like the way the constant doesn't matter. So similarly, we just derived it in the form of constant, right? So this value is a constant, right? So we would just leave this constant out.
Sir, I have a small doubt here.
Yeah.
Here you were saying that the base wouldn't matter for log terms, but
Yeah.
in the lecture, sir said we would always consider log to the base 2.
Yeah, that is why, I mean, see, most of the programs we would actually do by dividing it in terms of 2, right? I mean, if you have gone through the content, the merge sort is there, another many, I mean, some partitioning techniques are also there. So most of the times we will divide it in terms of 2 different subparts. So that's why we would consider it as base 2. But whether you choose it as base 2, whether you choose it as base 3, so let's say if you have done merge sort, so what you have done is you are dividing the array, right? Dividing the list in 2 parts, right? From here, and then from another part is from here to here. And then again, you are dividing it into subsequent halves. And likewise, you divide and you go, right? So merge sort can also be implemented by 3-way merge. So in that, you can just divide it into 3 separate parts. And then over here, again, 3 separate parts. Over here, again, 3 separate parts. So you can do that.
In that time, our algorithm would have log to the base 3.
3, correct. But does that matter in asymptotic notation? No. So here the algorithm would be log 2 base n. Here the algorithm would be log 3 base n. Correct. But whenever I am writing O outside, it would boil down to order of log n. And when I'm writing order of log n, now you whatever you want to consider, you consider. That's why it doesn't matter. You can consider 2, you can consider 3, e, whatever. Fine. But that would be equal. So I am not writing anything over here.
And that won't affect our efficiency calculations?
In terms of asymptotic notation. Fine. And we would deal in this course mainly in terms of asymptotic notation. We are not going into complex analysis of code. Those things are not there. So whenever a question is asked, if it's randomly asked that which code is faster, so let's say we have asked which code is faster, this 2-way merge or 3-way merge, right? Then you can say that my 3-way merge would be much, it is dividing much faster, so it would be faster. So you can say that. But if it is asked what is the time complexity of 2-way merge or 3-way merge or likewise any other example. So whenever it comes in terms of asymptotic notation or time complexity, right, either of the terms, if it is mentioned time complexity or if it is mentioned asymptotic notations, or symbolically order of O is given, or theta or omega, whatever is given. I'm coming to these definitions just a minute. But these notations are given, then you should always consider this constant does not hold any value. Fine.
Yes, sir. Thank you.
Yeah.
So does it mean for larger values, the more number of inputs we give, the time complexity becomes closer and closer for both of them?
You can say exactly that. Yeah, you can say that, but that is not somewhat mathematically quite true, because see, actually if you give a huge number, then the difference actually matters a lot. So mathematically, or by going by exact value of log base 3n and log base 2n, that's not something that would be correct, which would be correct. But yeah, asymptotic notations, it would be same. So don't confuse yourself with all those things. Just as of now in this course, we will consider asymptotic notation, so stick with that. Fine. So it's always asymptotic notations, and it does not consider the constants. So that's one thing. The other convention which is part of asymptotic analysis is we only consider the term which is the maximum term in the growth function. Growth function is what? Growth function is nothing but the function, the complexity function, which we described in the previous, this explanation. The function in terms of input size. So that is what we call the growth function. Why do we say growth function? Because that's how your program's time is growing. It is taking the time. It is consuming time as a function of the input size, which is represented by that graph. Which graph? The graph which is made by the function that you saw. So if I say the time complexity is a function of input size n, which is equal to say 2x4 plus 3x square, let's say cube, plus 1000 whatever x, right? Something like this. Oh, sorry, let's say this is x, the input size. Let's say some constant one. So whenever I write order of the time complexity, right? So this would be my fn would be, fx would be order of x to the power 4. Fine. We will only consider the term which has the maximum growth rate. What do we mean by maximum growth rate? Separate all the terms of this function, right? Now you have to see which particular term is increasing at a higher rate whenever the input size changes, right? So sorry, can you mute yourself? Hello. Yeah. So the easy way out is just simply see the exponent, or if it is a something like this, the exponential functions, right? 2 to the power x or e to the power x, right? X to the power x, whatever. These are the max terms. If some value is there which is exponentially at a higher level, like x to the power 4 is the maximum exponential value for raised to the power of x among all the terms, so then consider that. So whichever particular term is growing faster at a higher rate, right? Consider that. See, I'm not saying whichever term is greater, because let's say for x equal to 1, this value would be greater, right? This value would be much smaller. And that's why if you see the definition in the slide of asymptotic complexity, sir is actually telling that you consider something order of or theta of or omega of n to the power something or n, some function of n, after some value n greater than n naught. Remember this condition? In asymptotic complexity we have seen that. Let's go over here. Not this one. Yes. Right? Here. Right?
Sir, but if we have a constant that we have to reach only to certain number of input size, and if in that constant that function is attaining, that lower function is attaining the higher rate.
See, when you think of comparing algorithms, now the way is you always load it with maximum size of the input. I mean, you may have constraints that you will not go beyond certain input value. All those things are there, but those things are actually considered when some algorithm, see, some I'm telling you the thing, some algorithms are there. We would learn those things most probably in week 11 or maybe week 10, 11. Yeah, in those weeks we would learn that some algorithms are there which are, I mean, doesn't matter whatever idea you have. I mean, you would not be able to optimize it after a certain limit, and that limit is actually quite not acceptable. It takes a lot of time. Fine. So in those kind of algorithm which are not doable, I mean, till date, which are not doable at a faster rate or at a lesser amount of time, in those algorithm, what we do is we add some extra constraints. We do not consider the general problem statement. We say that, let's say, okay, this is very difficult to solve. It takes a lot of time, and probably there is no better way to solve it. So let's have some more constraints in this problem statement and see whether we can solve this constrained problem statement in lesser time or not. Right? So those constraints of lesser input size, relaxing the boundary conditions, right? Those things we consider when the algorithm is no way solvable in lesser amount of time. But normally we never consider those constraints. Always you should target your algorithm to be able to solve any huge size input in a given amount of, I mean, at a comparable or considerable time complexity. Fine. So while comparing, don't keep in your mind that you would only run this algorithm for so and so amount of input size. So why should I think of something else, or why should I think of this n0 and all those things? So, but yeah, that's not how we compare algorithm. Fine. Always think of it with huge value. Fine. So you see this n0, right? There is a bar n0 at this limit. After that, you say that the order of the big O or theta or omega, whatever, that holds after this n greater than n naught. So that actually is somehow reflecting this condition that if I only consider x equal to 1 over here, correct? So this term would be the highest term, right? And this term would be smaller. It would be only 2, and this would be whatever, 1, 2, 3, 4, 5. But when I take x equal to, say, 2 to the power 10, or let's say 10 to the power 10 only, right? Then what's happening? See, it would be 10 to the power 10, x is 10 to the power 10. Then my this term would be what? It would be 10 to the power 1, 2, 3, 4, 5, 15. But what will be this term? What will be the value of this term? It will be something like 10 to the power 40 into 2. See, it's much greater. So what is happening over here? At some point, the value of x to the power 4 graph was somewhere at a lower level, and 10,000x was somewhere at a higher level, right? But after a certain threshold value, which is n naught, right? This graph will go above, and this graph, it's not a graph of x to the power 4. I'm just giving you an example, right? This graph will go above, and this would go below. So ideally, you should always consider, what is this? This is your input size. So when you are saying now that I only have some constrained size of input, don't consider your algorithm like that. At least not in the, I mean, you should not do that at first. Always load your algorithm with maximum possible input size and then compare. Fine. So this is a obviously much faster increasing function, and your time complexity therefore should only depend on this function, considering asymptotic complexity. Fine. So
here our complexity will be O of x to the power 4 and not correct. O x power 5.
Acha, yeah, that I'm saying. See, that doubt was there. So it's not any O is what? O is the, I mean, you are going an up, you are doing an upper bound. So let's say if I have a graph like this, right? If I have a graph like this, so let's say this is a function. Fine. This is another function. This is another function. And let's say this is another function. Fine. This is my f1, f2, f3, and f4. Now, O says what is the definition of big O? Big O says that it's the it's the upper bound. The worst case, right? It's the worst case time complexity. That is, if I say F2 function, see F1 function is at higher level than F2, correct? This is time, and this is my input size. So obviously you can see, if I consider F2 and F1, F1 is at a higher level than F2. That means F1 takes much more time than F2. Correct? You can see that for the same input size, just draw a vertical line. Right? So this is the input size. So for this input size, F2 is taking this much amount of time, and F1 is taking this much amount of time. So F1 is obviously much more value. F2 is lesser value for the same input size. So whenever a function which takes more amount of time than another function, then that function which is taking more time, we can say that it is having an upper limit over F2, right? In this case, or upper limit over all the function which is residing below it. So in that case, we can write that F1 is an upper limit for F2. So we can write F2 as, you can write it in terms of F1, order of F1. Got it? So in other way, if let me give some example. In other way, it means if you have a function, let's say Fn is equal to n cube, correct? I can write Fn as order of n cube. I can write it as order of n to the power I, where I is greater than 3 or equal to 3. Now you would ask, I greater than 3 is still fine, but why I is equal to 3? My function was already n cube, but how can I write order of n to the power 3? So see, if you see the definition of big O, it says that any function f of n, I can write it as order of g of n, right? When some constant into g of n is greater than equal to f of n. Got it? So you see this equal to sign is there, right?
Yes, sir. But in this function, we're multiplying 2 times x power 4. So for any value of x,
what happens over here? I said now, when you consider asymptotic complexity, forget about
we'll ignore it.
Yeah. Only consider the values which are, so this constant is something else. This is a mathematical definition. Just see that the idea of n0 was so as to do not confuse. The very idea of n0 was to eliminate this factor. This huge constant in front of x was actually presenting this term as a greater term, which is not actually, right? This is the greatest term. So the whole idea of having n0, a threshold limit, is to eliminate any constant value that may present a term to be greater, which is not actually greater. Right? So we had a principle that ignore the constant. But if you relate that principle with the mathematical definition, then you would understand this having n0 property, this condition, is the mathematical way of saying you to ignore the constant. Hope you are getting the intuition, right?
Yes, sir.
Yeah. Okay. So that's why bottom line is, if you have any function of form n cube, we can write it as order of n cube, we can write it as order of n to the power 4, 5, 6, 7. But you can write it, but there is a bound. Theoretically you can write, but practically it's always better to write it in the nearest possible power that you can think of. So if we give you what is the time complexity for merge sort, right? And options are order of n log n, order of log n, order of n, order of n to the power 5. You take order of n to the power 5, because whatever be the function, order of n to the power 5 would be the cap on all of them. Log n is lesser than n to the power 5, n is lesser than n to the power 5, right? Whatever option. So that's not a way to answer the question. right? So you should give the nearest possible estimate for that algorithm. But theoretically, you can say. And there is another concept of loose upper bound and tight upper bound, loose lower bound and tight lower bound, but those things are not there in the syllabus. So as of now, you can say that you can write anything. I mean, that's not a problem. And those things are not that much relevant also, so it's fine. Yeah. So this is okay, right? You can write it in this form, no problem. But only thing, you should not write it from the exam perspective. If you write in exam that order of n to the power 5, because you will say that all other options are actually something below order of n to the power 5. That's why I take the order of n to the power 5. You will not get marks. You should give the nearest value of that algorithm. Fine. Okay. Okay, so this was done. Another thing was what is O, theta, and that omega. So we just discussed this thing, right, in a graph. So if you have a graph, fine. What is O saying? O is the worst case time complexity. What is O? Big O is worst case. That means, see, this is time, huh? Never forget, this is your time axis and this is your input size axis. Fine. Now, O is worst case. So what does that mean? That means it should be some function somewhere over here or whatever, right? If I want to say that that particular function is bounding, I mean, capital O of that function is bounding f1, f2, f3, or I should be able to write something like f1 is order of that function g, right? Let's say this is g, this function, whatever. Then I'm writing f2 is also order of g, f3 is also order of g. Then the only thing is I must have g on top. That is, it is bounding as an upper limit of all the function, and that's why it is the worst case. So if you see, g is taking the most amount of time, correct, for a same input size. This is the input size, right? Input size, is. So that's why I should be able to write order of g if and only if g takes much more time, or g is a higher, I mean, g is increasing at a greater rate than f1, f2, and f3. Then I would say order of g. So what is this? This is the worst case, that g is worse than f1, f2, f3. Worst among f1, f2, f3, sorry. Correct? Now comes the best case, which is my omega. Right? What is best case? Now best case is something which is actually at the bottom, just the opposite. So in this case, you can say f3. Right? So any algorithm which takes the least amount of time as compared to its partner, I mean, which is the lower bound, you can say that as the best case time complexity, which is taking the least amount of time. So I can write something f2 equal to omega of f3. Fine. Similarly. And now what is theta? Now these two are simple. Now what is theta? Theta is the average case. Now this is the average case. Now this is a little bit more, I mean, you have to think about it a little bit. I mean, not mathematically. Mathematically, it's obvious it would be something between order and omega. I mean, big O and omega. But that's not what we want to discuss. What we want to discuss is what is the need of this case, average case. I mean, what do we mean physically? What do we mean by that? When you think of an algorithm, either way, one way you can think is I have to compare it with other algorithm and see it whether it is the best performing or not, or the other way is whether it is the worst performing or not. But why do we need to think of an algorithm whether it is in the average case or not? Right? Can someone tell? Can someone think of any?
Sir, because average or best case or the worst case may be rare in some inputs.
So, yeah.
It's like outlier and Bell diagram.
Bell diagram. Yeah. So I cannot explain it in terms of Bell diagram, but that was nice. Nice example. I mean, in this case, over here because all of us are not aware of bell. I mean, all of you know bell diagram?
No.
Yeah, it doesn't matter. Okay, no issues. Yeah. So fine. Yeah. Okay. So see, the basic idea of average case is, let me give you a practical example. Whenever you come, I mean, all of these discussion we are doing just to select from a basket of given algorithm which one is better, or in other words, when you are thinking of different approaches to solve a problem, you should be able to analyze and pick up the one which is most suitable for your need. So we are actually now learning the tools to analyze the algorithms that we would be learning in the subsequent weeks and also in this week also. So that is the main idea. So worst case, best case is quite intuitive. You may think it in terms of whether my algorithm is best performing, or you may think it, okay, what is the worst performance that my algorithm can do? If I can say that this is me at my worst, whatever comes after this would be something that is better than this. So if you can accept me in this worst scenario, you can accept me in the future as well. So that is actually a better way to sell your product, right? That this is my worst scenario. If you like this, then obviously you would like what may come in the future. So what I mean to say exactly is, if you give a particular input to a problem, now please pay attention over here. There is no algorithm where we will only consider worst case or where we only consider best case. Rather, what we do is we take an algorithm, we change different inputs to that algorithm, not only the size, but the way that input is given. I mean, what is the input exactly, right? There can be multiple input with different logics, I mean, in that input, correct? So we give those inputs and we check whether the performance of the algorithm changes with respect to the type of the input. Even the input size is same, right? Just a second.
I have a confusion when you say input. So input is about the data or it is about the steps involved in the algorithm?
No, it's about the, I mean, that not the steps, the data. Did you get it? Hello? It's about the data, huh?
Yeah, it's not related to component of algorithm, right?
No. You have an algorithm, right? And now we are not going to the size. While comparing best case and worst case, we are not comparing it in terms of the size of the input. Rather, we are comparing it on the type of the input. So let's say you have a sorted algorithm. I mean, sorting algorithm. In that sorting algorithm, it is sorting in ascending order. Now, one possible input can be a list which is already sorted in ascending order. Another possible input can be a list which is reversely sorted. Another possible input can be a list which is totally random. Another possible input can be a list which has all the elements as the same element. Right? So all these inputs are different types of input. Let's say all of the inputs are of the list are of like length 10. So the length I'm not changing. It's a list of length 10, but all of these inputs have some different ideas, right? Some logic, some property, not logic, some property which is there. So how does your algorithm performs when different different inputs with different properties are given to your algorithm? Does it perform in a particular input? Does it perform very bad? In a particular input, does it perform very good? Right? Or does it perform in all the input? It performs at an average level. Right? So that is what is to be judged. Now, most of the algorithms, it would have certain logic, right? And whenever you proceed with a problem with a certain logic, it tend to have some better performing cases and some bad performing cases, right? So some input size, the same algorithm, sorry, not size, why I'm saying size, some input the same algorithm would perform good, and other input the same algorithm would perform bad, right? So in these kind of scenarios, worst case and best case come. So if I say it, for same algorithm, There are best, which is my omega, and worst cases. Cases mean types of input. Please underline, notice this underline. I'm again saying types. I'm not comparing the size of the input when we are considering best case and worst case. What I'm comparing is I'm laying stress on the word property of the input.
So in all cases, size of the input will same, right?
Exactly. But that is the correct way to compare your best and worst case for the algorithm. See, if you change the size, then it would take much more, it would take some more time to calculate that size, right? So will it be a good idea to compare, like someone said, you would be comparing apples and oranges. So whenever you are comparing on a specific property, you should not change another property. It's a common thing in in many mathematical analysis, which we call the invariant, that when you are comparing two things or analyzing two things and you want to see how the final product changes when you change either one of these two things, right? And also you cannot isolate both of them. So it's better to keep one constant and change the other one only and see what changes occurring on the outside. If you see the output is changing by, if you see a pattern of change in the output by keeping one variable constant and other variable dynamic, then you would be able to understand that how much the output change with respect to that particular variable. So here there are two variables for input. First is the size. Second is the property of the input. The thing that I said, it can be reversely sorted, it can be repeating, it can be, different types. So it can be random.
So do you think like there could be another word for this property of input? I suppose like there could be some other word. Size of input is fine, but property of input, the example which you gave us,
yeah,
related list. Do you think like there could be more suitable word for this property of input?
Generally we denote it with worst case and best case only. So we say that this input is the worst case for this algorithm. This input is the best case for this algorithm. But I don't know any better word to say that, right?
Okay.
Yeah, I'm not aware of that, if there is any specific word. But yeah, that's the concept. Fine. Yeah, you want to say something?
No, it's clear now. Because earlier like input word was a little confusing.
No. It's please clear all your doubts over here. This may seem trivial, but this is very important. Otherwise, the concepts, algorithms you would understand. If you read also you would understand. But these concepts are very important and you should be crystal clear in your mind why we are going into these things. Otherwise, later weeks, you would not be able to reason while comparing. Okay.
And will you explain average case again? There was little confusion in terms of comprehension.
Okay, so every case means the order of omega, these three things?
No, average case.
Oh, average case, average case, okay.
I can see the Bell diagram in my imagination,
no.
but it's still like, yeah.
I got it. So I was just telling that. So there can be best case and worst case, that idea is clear, right? Now see, some algorithms can perform that whatever input you give, right? Whatever input, doesn't matter. Whatever input you give, it would always give you the same complexity. Mind it, I'm saying complexity, I'm not saying time. We have done asymptotic complexity, and now please forget about second, millisecond. When I'm saying time, I mean function in the form of n, which is the input size, correct? So there can be some algorithm which has no best or worst case, whose best case and worst case are same, right? No is a wrong word. Whose best case and worst case are same, because whatever input you give, irrespective of that, it produces the output. For a particular size of the input, it produces the same output, irrespective of the property. Wait, irrespective of property, produces same timing for a specific input size. Yeah.
So this average case is also like a theoretical computation.
You can say that. You can say that. So the practical idea is this thing. Whenever you have an algorithm, irrespective of whatever type of input you give, assuming the size is same, right? Whatever input you give, it produces the result in same timing. I would say that particular timing is the average case for that algorithm. It essentially means that algorithms worst case and best case are same. There is no difference among these cases. Now, if I give you an example, merge sort is one such algorithm. So irrespective of whatever type of input you give to merge sort, it would always take order of n log n time.
So we can say this is a perfect example of average case.
Exactly. Fine. So the best case of merge sort is order of n log n. The worst case of merge sort is the worst case of merge sort is order of n log n. The best case of merge sort is omega of n log n. The average case of merge sort is theta of n log n. But when I come to some other algorithm, so let me give you an example of, let's say, insertion sort. Fine. Insertion sort, the best case would be, can someone tell?
First element, inserting.
What? I mean, you have to tell some function in terms of n, right? Sorry, repeat.
Yeah, sorry.
Yeah, someone was saying, someone wants to say, but this best case, right? What is the best case? I mean, let's say you gave insertion sort some input, and that input is the best input for insertion sort. I mean, if you give that input, insertion sort would give you the result immediately, much faster, right? So how much time would insertion sort take in that sense, in that case, sorry, in terms of input size?
Sir, n?
Correct.
Only one? Oh, okay.
Order of, I mean, omega of n. Why? Yeah. So we will come, right? I am coming to that, just a second. So, acha, and so what is the worst case?
N square, sir.
Correct. Fine. So here we have best case and worst case as different values, and average case is a function which would lie between n and n square. You cannot, I mean, you can theoretically measure it, but since the best case and worst case for these algorithms are different, right? So you can say that average case, a definite average case does not exist. The constant values would change. So if you see the definition of theta, right, theta's definition, I can write something as theta of f of n, g of n equal to, right? So when I can say that c1 into f of n fine, so these constants are there. Obviously, for you all know these notations, right?
For all n.
Yeah, so I hope you have learned this in set theory.
Yeah.
Yeah, okay.
So, one doubt here, like you are representing best case in terms of this particular sign omega, and worst case in this big O. So is it mandatory to represent in this particular notation? Like, can we represent best case in big O and worst case in omega?
See, best case is represented using omega, and that is a convention. Worst case is represented using big O. But let us wait. But if the question, right, in order to, I mean, this is the way it is. This is the conceptual knowledge, and please learn this thing. But in your, I mean, in the assignments or in the quiz, maybe, if it is given that in the question that what is the best case time complexity for this algorithm among the given options, right? And in the options, it is given option A, order of something. Option B is also order of something. So all the options are in terms of order of. But in the question, it is stated what is the best case time complexity for a particular algorithm, choose the correct option. But the only thing is the options are given in terms of order of O, right? So please ignore this order of O. There are some problems that may come, and yeah, sometimes you may see the best case also written in terms of order of, I mean, in big O notation in the option. So please ignore that and give your answer on the basis of the function which is given here. But for your knowledge, please keep this thing in mind. Best case is always represented with omega. Fine, is it clear?
Yes.
Okay. Fine, so this is your best case, average case and worst case. And now the idea is why we will only consider worst case in our long run. I mean, at least for analysis. As I told you once that the idea is if you can tell that this is the worst possible scenario, I mean, this is the input corresponding to which my program would perform very bad. I mean, it cannot perform, I mean, worse than this. It is the worst performance that I can give you. If you can sell that to a, while selling that to a person, to a, I mean, to the client, your software, right? If you tell that this is the worst performance, anything, any type of input comes in future, I would give you a better performance than this. And that is always good, right? I mean, and that worst performance is acceptable to you, to your client, then he can be very happy. Okay, even the worst is acceptable to me, so obviously the better cases would be acceptable to me every time. So I can be assured of that. Fine. So that's why we will always consider our algorithm in terms of order, or the big O notation, and we would rarely use the omega notation and theta notation. And mostly if we use, we will use in this week only to understand or discuss the concepts. But in real life analysis, mostly we discuss the worst case notation, that is the big O notation. Fine. Okay. So any doubt in big O or why we go for asymptotic notation, these things?
One doubt. I missed the first session, 20 minutes. So I just have a doubt. I'll clarify. So
Yeah.
we are finding out this omega of n or O of n square depending on the loop, right? Iterations.
Depending on the iteration. Yeah, loop can be there, recursion can be there.
So
if
there are two loops like iterations or whatever it is, if it is like two loops, so it will be automatically O of n square. The worst case will be, right?
Correct. Yeah, the number of iterations.
Yeah. Okay, thanks.
So the idea of asymptotic analysis is based on the size of the input and the number of steps that we are taking to, the algorithm is taking to perform, I mean, give the result. The idea of big O or omega or theta, which is a part of big O, I mean, which is a part of asymptotic notation, is we consider different types of input, keeping the input size same. Right, so there are two levels. The first level is, since system dependency and language dependencies are there, therefore we should not directly consider the time taken by an algorithm in units of time, which is second, millisecond, or whatever. Right? In order to eliminate all those, we use a tool of asymptotic complexities. Now, asymptotic complexities has three different types: big O, omega, and theta, which is my second level. And this second level deals with keeping the size constant. My first level was keeping the size variable. I mean, you are comparing algorithm on different input size, right? It was a function of the input size. Where is my cursor? Yeah, it is a function of the input size. But when you come to the big O, I mean, these three different segregation, the omega, theta, and big O, then we are not considering the input size, rather we are considering the, for a lack of better word, a property of different input of specific size for a specific algorithm to find which particular input when given to that algorithm would be better and when it would be worse. Once I find that, I would choose the big O among them. Why? Because if my worst case is acceptable to you, I mean, then whatever input may come in the future, that would also be acceptable to you. That was the gist of it. Fine.
So that is kind of least expectation.
Least expectation. And if that least expectation is also, I mean, you are quite happy with that, then obviously you would be happy in the future. So you go and buy that software. Fine.
One thing I missed. I mean, you were comparing with, you know, time with complexity.
Yeah.
So we don't think in terms of time, but we think in terms of complexity, right?
Correct.
And what was the reasoning behind not accepting the time? I just missed that.
I explained that in detail. You can check that, but the basic idea is in order to eliminate the system dependency and language dependency. Fine.
Okay.
It's given in detail. You can just go and check in the YouTube, right?
Okay.
Fine. Okay. So next we will move to the next topic. This topic must be clear by now. So, so order theta, that is done, and which sorting? Which sorting was the next topic? How to think. These are some exercises which are there. You can check all this. Obviously, see, these are 3 loops running as from I to n, ij to n, k to n. So since this outer loop, obviously all the inner loop would run corresponding to the every time corresponding to the just outer loop, and then j loop would run.
Where are these codes? I couldn't see.
These are actually in that wiki page, that PDSA wiki page. That's there.
Okay.
It's there. You can check all that. So these are just some. It's kind of a gist of all the thing, a notebook kind of thing. Like generally the wiki thing is there. So in that. Fine. So these are some sample worked out problems. You can check all those. How much time does it take? Simply loop and iteration, all those things. So you are saying loop, right? So this is, see, here we do not have any loop. We have only recursion, right? So when we have recursion, what we do is we basically form a recurrence relation. Let me give you an example. So what we do is every time there would not be loops or normal coding. So recursion is also a way in which you can think of analyzing your time complexity. So let's say I have one function f of n, right? Let's say it is doing some task over here, and here at the end of the function it's calling itself, but the value is n minus 1. Fine. So let's say here it was running a loop which was running from I equal to I from 0 to n. Fine. Correct. So over here. So what will happen? What is the time complexity? How will we do that? So whenever there is recursion, whenever you see recursion, if it is a simple loop, multiple loops, nested loops, whatever, right? You can just think of it. I mean, okay, so this is iterating so many times, this is iterating so many times, and you can think of the idea how you can formulate the formula for complexity. But when recursion happens, the way out is what you can do is simply write it in the form of a recurrence relation. What do we mean by recurrence relation? So f of n is calling f of n minus 1. F of n minus 1 would call actually in value f of n minus 2, right? So what I would write is the time taken by f to solve a problem of size n is equal to the time taken by the same algorithm to solve a problem of size n minus 1, right? This n minus 1. So whatever time would be taken by this whole algorithm would be equal to the time taken by this part plus the time taken by this part. Correct? Now this is the part corresponding to this one. I do not know what is the time. That's why I've written it in the form of t, right? But this I know. This is a loop which is running linearly from 1 to n. I mean, yeah, 0 to n minus 1. Right? So it is running n times. So I can write it as plus n. Correct? So you can write it as t of n minus 1 plus n. So let's change this. Let's assume that this was not n minus 1, rather it was something n by 3. Fine. What would be the recurrence relation? Same idea, t of n equal to t of n by 3 plus n. Let's say I say it's t of n by 3 plus f of n by 2. Right? What would be the recurrence relation? T of n equal to t of n by 3 plus t of n by 2 plus n. Correct. Now the problem is you have to solve this recurrence relation. How can you solve it? Now, very complex recurrence relation would not be coming into the questions. Simple recurrence relation would come, like this may come, something like that, where you can do substitution and solve it. How to do substitution? Just simply replace this t of n minus 1 by putting the value of t of n. So we know t of n is equal to, I mean, if I, let's delete this. T of n equal to what it will be. Before going for that, I'm writing t of n minus 1. So if I put over here in this equation in 1, if I put t of n minus 1 over here, what will happen on the right hand side? It would become t of, this is t of n minus 1, right? So in place of n, I am putting n minus 1. So n minus 1 minus 1 plus n minus 1. Fine. So this is essentially t of n minus 2 plus n minus 1. Fine. So this is what I would put in over here. T of n minus 1. This is right, this place. In this place, I would put this value. So it would be t of n minus 2 plus the leftover. So this is one level. So if you go on repeating this for k number of times, you would see what is happening here is every time you are deducting by 1. N minus 1, n minus 2. Here it was essentially n minus 0. Correct? N minus 1, n minus 2, n minus 3. Likewise, it will go down. So what is happening? At one stage, this n minus, it would go to t of 1, which is constant. And this would go from n minus 1, n minus 2 up to 1. Right? Just extrapolate it. It would be something 1 plus dot 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 plus n minus 1 plus n. So this is just a summation. Right? You know that it's n square. Correct? I mean, on order of n square, if you do n into n plus 1 by 2, that is n square plus n by 2. And in asymptotic complexity, we only consider the highest term. So it boils down to order of n square. So likewise, this similar kind of recurrence relation may come, but nothing difficult would come. But just for your information, and if some of you are interested, there are multiple techniques to solve recurrence relation. Fine. Just like in your calculus classes, you all have learned how to solve have you learned how to solve differential equations? At least a little bit?
No, sir.
Okay.
Yes, sir.
Yes, yeah.
You have
It was in
learned.
class 12th. Yeah.
No, not class 12. I am asking you in this course.
Yes, maths too.
Yeah, everyone would have completed maths.
Fine. So all those who have completed, you must have completed. So yeah, so those in maths too, you all have learned, right? In how to solve differential equations. So recurrence relations are also called differential equation of discrete world. What is discrete world? So this is a part of mathematics which we call discrete mathematics. Fine, and that's why you can call recurrence relation as differential equation of discrete mathematics world. So there are as much as defined ways, like in calculus we have learned there are multiple formulas and ways to solve differential equation. Here also there are multiple formulas and ways to solve differential equation, even to solve this recurrence relation. Even we also call it in the same terminology as homogeneous solution, right? Those exact terminologies are used. So if someone of you are interested, you can check that out, but those things would never come as a part of this course. All you have to do is do this back substitution multiple times and then arrive at a general equation and then solve the complexity. Fine. Is it okay? Any doubt? Fine. So the point is, you can have complexity not only tested on the basis of loop, but also tested on the basis of this recursion and other things. Fine. Okay. So likewise, you see the merge sort complexity of recursive solution. Okay, so now we are moving into sorting and searching. Before sorting, I want to do the sort because that would take a little more time. What I would do now is I would just go through the basic idea of different types of sort, and then I would discuss how to think that one of you questioned that which one to take, which one to apply when you think of a real life problem. So that I would address. And in the process, if you have any doubt, particularly to a specific sorting algorithm with respect to the slides and the lecture, you can ask at that point only. Huh?
I have a question here.
Okay, yeah.
I mean, up to now, like our focus is more on what, not on how. So do you think, like, I mean, I'm not totally aware about this entire PDSA program. So
okay.
Like, we'll be doing the calculation about like how also?
Can you be a little more specific? I mean, how means what are you expecting?
No, so here, like, we are talking about like, what are the complexity, correct?
Yeah.
And we are talking about complexity design.
Yeah.
So that you can reach to some solution.
Exactly.
And this is all theoretical, right?
Yeah.
But let's say like if you write some algorithm and you
exactly.
have to calculate like exactly how much time it will take or what is the complexity.
Yeah. Yeah.
So will we go into that calculation also?
Yeah. I mean, you are doing that, right? So what was these questions were about? I mean.
No, so this is all theoretical because we don't figure out like what would be the function or what would be type of function.
I mean,
this is all given.
You are telling that when you see a problem, you would think of an approach and then analyze how much time it takes, right? Something like that.
Mm-hmm.
Yeah. So that's what I said. Now, see, whenever you are learning a course, I mean, the lecture content has a specific time limit. So we cannot actually always go from naive solution to the best solution. But that's how you should think. I mean, I mean, in live session, always we would do that, at least in the live coding. We would try to do that. Think about the naive solution, incrementally improve upon that by analyzing the complexity. But if you say in terms of lecture, if you describe the naive solution, then do everything, it may not be possible in half an hour lecture. So we basically go for the best approach which is there for all the algorithm. But that's a request to all of you rather than a demand that you should think of the algorithm by seeing the problem statement. What comes to your mind? How can you solve it? Then you see the lecture how it is done in a better way. Fine. And yeah, in live session also, anytime you all can come up with any algorithm for any problem or any other problem. I mean, any kind of problem may be discussed as a part of lecture or maybe discussed as a part of the live session or any assignment. Please go ahead and explain, and we would discuss that. Okay, if this is better or whatever it is, right? So anything, whenever you see an algorithm, you have to think how to analyze it. So it would be going in hand. But yeah, maybe in the lecture it's not quite possible for time boundation.
Okay.
Yeah. So what I was thinking, sorting. So like here only we will discuss. See now, I mean the algorithms. But if you're trying to think of a new algorithm and then discuss, then you have to go to the problems. Once we go to the problems, then you can argue, okay, this approach is faster, that approach is slower. Those things will come. Okay, so first we will discuss, let's say, selection sort, or no, first insertion sort. I would only briefly discuss this because these are part of the lecture's content. So how we do insertion sorting generally? Let's say if you have an array like this, fine. I have 2, 4, 7, 1, 8. Something like this. Fine. How insertion sort would work? Insertion sort would first see whether the first number, this first number is, it would keep it as it is. It would first check for the second number. Whether the second number, let's say I'm going for ascending order. It would check whether the second number 4, whether it is lesser than the previous number, whatever is behind 4, whatever is on the left side of 4. Now in the first iteration it is only a single number, but in the subsequent iteration there can be multiple numbers on the left hand side. Fine. So insertion sort always checks the current number on which the arrow is there, right? What is the correct position for that number on the among the elements on the left hand side? So what is the correct position where to place the current number on which my arrow is there among all the elements on the left hand side? Correct. Now why on left hand side? Because we assume as we proceed through the algorithm, as we would show, the left hand side would be a sorted list, the sorted part of the list, and the right hand side would be the random part, right? So see how the algorithm would proceed. First it would see 4, whether 4 is lesser than 2 or not. 4 is not lesser than 2. So in the next iteration it would keep it as it is, 2, 4, whatever is there it would remain same, 2, 4 dot dot dot. What is the next element that it would compare? It is 7, right? 4 is done. So 7 is the current element. Now see on left hand side I have 2 elements, 2 and 4. Correct. So it would see where to place 7. So first it would check with 4. Then it would see that 7 is greater than 4. But we are assuming, not assuming, we are proceeding in the way, right? From left hand side everything is sorted. So do I need to check for 2 also? No, right? Because we have already checked that 7 is greater than 4. So I'm not taking 7 on left hand side anyway. So 7 would remain at its position. 2, 4, 7. Okay. So 2, 4, 7 done. What is the next element? 1. Fine. Now it would check what is the left element. What is the correct position of 1 among all the elements on left hand side? It checks with the first one over here, whether 1 is lesser than 7. Okay, we got 1 is lesser than 7. Whenever 1 is lesser than 7, whenever your current value is lesser than the first value on left hand side, you would do a swap. Fine. So what I do is 1, 7. Fine. So swapping done. Next thing is again we would check whether the next element of 1, I'm only placing 1, right? 1 was over here. So I'm placing the 1 at its correct position. So where 1 should be located on the left hand side? So it checks 1 with the next value, which is 4. Is 1 lesser than 4? Correct. So again there would be a swap. So 1 would be coming here, 4. Fine. And again it would check whether 1 is lesser than 2 or not. And yeah, it's lesser. So it would put 2 and 1 here. So again there is a swap. So you see, every time I proceed like this, now it would consider for 8. Correct. So every time I proceed like this part of my array is sorted, the red part. See, 1, 2, 4, 7, it's a sorted one. Previously only 2, 4 was there, which was also sorted, right? And then 2, 4, 7 came, which was again sorted. And now it came 1, 2, 4, 7, which is again sorted. So every time the left side is always a sorted list. So what I'm basically doing is I'm putting an element from the right side, which is the random part, and placing that element at its appropriate position among the sorted part. So at the end of the day, the sorted part increases and the random part decreases. And finally, we cover the whole array as the sorted array. I mean, make the array as sorted. That's how insertion sort works. How do we call? Why do we call it insertion? So basically, you are picking a number and inserting it at a proper location on the left-hand side. That's why we call it insertion sort. Fine. Now my question is, as you were saying, what is the time complexity? We just discussed it earlier. The best case time complexity was, I'm writing as of now with omega notation only. But yeah, you should, as I said, that in the options, if it is giving in terms of O, and in the program, in the question text, if it is asking you what is the best case complexity, then please ignore the O notation in the option and only give your answer on the basis of the function given. Yeah, so the best case, what would be the answer?
0.
Why 0?
Already sorted.
Yeah, if I give you a sorted array, one, let's say for a smaller example, if insertion sort is asked on a, let's say 4 element, and which is 1, 2, 3, 4. What will happen? It would first check 2 with 1, right? Correct? In order to understand that 2 is greater than 1, it has to be checked. There should be an if condition. If,
so linear.
Yeah, if ARR of I is lesser than ARR of I minus 1, then you do something. That is basically swap. And now this swap would not be a direct swap, there would be a loop also, right? Because we are doing that for multiple number of elements, but just for the idea, you would write here, then you would do the swapping. Right? Otherwise, else you would proceed over the array. Oh, sorry, over the list. And what do I mean by that? Since remember 2 and 4, when it initially it was 2 and 4. So when you are checking, okay, 4 is already there. So how do you know? You first compared it once, right? Without comparing, you don't know. Then you proceeded to 7. So this if condition, this comparison must happen. So this takes some order one time. Correct. So at first you checked whether 2 is lesser than or greater than 1. You checked and you got the result as 2 is greater than 1. So I do not need to swap. Fine. Next element is 3. So how much time went into this comparison? It was order of 1. Right? One if statement, order of 1. Next comparison with again 3 and 2. Whether 3 is lesser than 2 or not. You see, okay, no, 3 is again greater. So this comparison also took order of 1. Same if case again repeated, order of 1. Then you check this, and same if case is again getting repeated. Now if case is taking constant time, order of 1. So you again took order of 1 over here. So you are not swapping, you are checking, but checking also takes some time, which is a constant time. So you are correct in spotting the constant time, but only thing is you did not consider the number of times that constant time is getting repeated. How many times this comparison would go? It's taking n-1 time, right? If n is the size. So essentially your total time is n-1 into order of 1, which boils down to order of n-1. We do not consider constants or any value, so it boils down to order of n. Fine, sorry, whatever I also wrote in order, it should be best case, because I'm only considering best case over here. Right, so the answer is best case of n. Got the idea? Because this comparison must happen. Otherwise, how will you know whether 2 is greater than 1 or not? Right. So that's it. So omega of n is the best case for insertion sort. And if you go for the worst case, I mean, what will happen? So in that case, you have to check all the element, right? So what will be the worst case? We discussed that worst case and best case means different properties of input that you give to the program of a specific size. So this property was already sorted. What would be the property of an array that would give you the worst case?
Descending order.
Correct. It would be the other way around. So 4, 3, 2, 1. What will happen now? 3 would be checked with 4. Yeah, I have to swap. So swap it. Right? 4 would come here. 3 would come here. So now this swapping time is also considered. Fine. Now again you compare 4 with 2. You see again, yeah, I have to sort. I have to swap. So 4 would come here. 2 would come here. But 2, there is another element on left hand side. I said that you have to compare with all the element on left hand side. So 2 has yet not finished. So again you check for 2 and 3. You see, oh, 2 is again lesser than 3 also. So you remove 2, write 3 over here, write 2 over here. So again a swap. Fine. So for every element from the random part, you have to carry it forward to the end on the sorted part if it's in the descending order. What the idea? I mean, every time you have to take it to the last, because if you see, if I have 1 at the last, here 1 is there now. So you have to again compare all the element and swap, and at the end 1 would be at the first element over here. Right, so what's happening actually, for every element that I get on right hand side, I have to compare with all other elements on the left hand side. So the last element 1 would be compared with n minus 1 element. The second last element, the 2, which was initially 2 was there, right, would be compared with n minus 2 element, plus dot dot dot. The first element 4, which was there, sorry, 4, 3 was there, right? 4, 3, 2, 1. So 3 would be only compared with 4, and then it would be swapped. Remember? It's getting messier. Yeah. So three just got only one comparison, and then it was swapped. 4 was put over here, 3 was put over here. Only one. So last case would be 1. Right? So n minus 1, n minus 2 plus dot 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 plus 1. This value is again your summation up to first n minus 1 term, that is n minus 1 into n by 2. Correct? So if I consider it in terms of order, it is n square. Because this n into this n, order of n square, right? We do not consider constants, so eliminate that. We do not consider n. So another term would be n square minus n, right? Now n is a smaller a term which is growing at a lesser rate that we just discussed above. So I would only consider the higher function, which is n square. So the worst case time is order of n square. Fine. So that is how we consider best case, worst case insertion sort. Now my question is, now you have to answer. This is the basic algorithm. And for those who did not see the lecture also, I want you all also to participate, and that was the motive of us giving you the basic idea of this algorithm. You all know binary search. I mean, those who have seen the lecture, right? Can you tell me what happens if we do binary search while choosing the proper place to position the element on right hand side? Every time what I'm doing, I'm taking the element over here and placing it at a proper position on the left hand side. Our left hand side is sorted, right? You remember, every time we are putting the left hand side array is, I mean, the left hand side part of the list is a sorted list. So if it is sorted, I can do binary search. So why I am checking 8 with 7, 7 with 4, I mean 8 with 4, 8 with 2, 8 with 1. Let's find the proper position to put 8 and end it up there. Just put 8 over there using binary search. We do not have to do linear search. So will that improve the complexity? Will I get a worst case complexity is better than n square? Can I get something like n log n maybe? Using insertion sort and binary search combined.
But sir, we still have to change the position of each element by 1 to the right side.
Correct. Very good. Yeah. So you can do that algorithm, but at the end of the day, you would always end up with order of n square time only. The reason for that is, even if you use binary search and you point out the proper place to put the value that you are currently considering, but you ultimately have to swap the other elements or create space for that element to be put in between. List is a continuous memory, right? You are having those elements. So if you are trying to modify that list by putting some element in middle, right, what will happen is the system would again create another list internally and it would copy all those things over there. Or in other words, you would have to shift all the elements on right hand side. If you want to put some elements at a specific place, then all the element on the right hand side should be shifted right once, so as to create the space for that element to be put. Got the idea? So that would, at the end of the day, shifting all those elements by one unit to create the space for putting the element that you are considering on the right hand side would take order of n time, right? Because you are shifting each and every element. So what happens in the worst case, in this 1, 2, 3, 4 case, you have to shift all the element by right hand side by one unit in order to create the space for one to be put here. Got the point? So even if you use binary search, you would not get a complexity which is lesser than n square. So worst case of insertion sort is n square. Fine. There is a common question that comes, that when you use binary search with insertion sort, can you get a better complexity? Right. Next is selection sort, and now we will do the comparison thing would come. And there is a very interesting observation that I would like you all to point out. Compare selection sort and insertion sort. So how selection sort happens? It's it's rather easier. So what you do is you have these cells, right, in the array, in the list. So 0th, 1, 2, 3, 4, 5, 6. I'm not writing the values. That's not quite important over here. How selection sort works is, let's say this is an unsorted array. Fine. It would consider all the element starting from 0 to 6. I mean the end of the index, and it would just find the maximum, or sorry, minimum. Since you are doing in ascending order, it would find the minimum. Find min. What is the index? 0 to 6. Right? Once you get the minimum from 0 to 6, what will you do? You would just swap that minimum with the element at 0th position. Right? 0th, let's say the 4th element is the minimum element. Right? So what will you do is you would swap 4th element and 0th element. That's it. Fine. So what I can guarantee is, after the first iteration, my first element is the minimum element. Next iteration, what I would do is I would run from 1th index to 6th index. Correct? So this is iteration 1, this is iteration 2. Again, same objective, find minimum, but now 1 to 6. Remember that the element which was initially there at 0 is copied at the 4th index now. And the minimum element which was found at 4th index is copied at the 0th index now. So now I got the minimum over here and I am just segregating this part of the list. My search is now on this part. So 1 to 6. Again, I find the minimum, and this minimum is obviously the second minimum, right? I would say the second lowest value. Lowest value was this one. Second lowest value would be now the one that I that I get now. So I would place that over here. So second minimum. Fine. And again, you segregate this part. Now you test from here to here. So what we are doing in selection sort, basically, we are finding the minimum in the sub part of the array by decreasing the array size one by one. And every time I am finding the minimum, I am placing that accordingly in the 0th cell, 1th cell, 2nd cell, 3rd cell, 4th cell. Fine. So basically in selection sort, you are picking the elements, picking the minimum element and placing it at its best, at its proper position. Fine. So finding selection sort is just writing the find minimum code in a loop. That's it. And then doing a swap. Selection sort is nothing but find minimum code written inside a loop with a swap statement. That's it. Fine. Is it clear?
Yes.
Now my question. Can you compare if I ask you the number of swapping, not the number of comparison. So there are two things that are going on in our sorting. Any sort, the comparison based sort. So what are comparison based sorts? You can assume all the sort that we are learning now are comparison based sorting. And there are other types of sorting that's not required as of now. So any types of sort that we are learning, there are two fundamental operations that is going on. The first fundamental operation is comparison, which is achieved through your if statement, whether some ai is lesser or greater than aj. J can be also I minus 1, I plus 1. I'm not going into that. My basic idea is comparison between two elements using if statement. Second, root operation. These are root or fundamental operation. Fundamental ops for sorting. Right. Second is swapping. Right. So once our if statement gives a true result that okay, this is lesser than that or this is greater than that, if that is favorable for me, I would do a swap. So the ultimate all comparison based sorting boils down to two fundamental operations, comparison and swapping. My question to you is, as you are telling what are the differences between different types of sorting, how to think about it. If I tell you there is a system in which the swapping operation takes a lot of time, but comparison is faster. Among insertion sort and selection sort, which one would you apply? I'm telling you, swapping takes more time. Swapping takes more time.
Insertion sort, sir.
Selection sort, sir.
Both of them, you should give your reason.
So in the insertion sort, the thing is, if we find an element which is greater than, then we have to like swap it in the couples. Like if there are 4 elements, 4, 3, 3, 2, 1, 0, if there is a case. But in this, if we find an element, we already know that the smallest element is at 0th position. So we'll swap only once.
Correct. Yeah, correct. So I'm giving the correct answer. So that's the thing. I'm just restating it. What's happening is insertion sort. Let's go to that diagram once. What was happening? Right. I will just give this example only. So you have an array 4, 3, 2, 1. Worst case. Right. So what was happening? I was comparing over here. So this is my compare. And let me use another color. So a black color. And again, this was my swap because this comparison was fetching a true, right? 3 is lesser than 4 and I want to do a ascending sort. So this was my compare and this is my swapping. So one swapping happened. Again, let's see. Again, I compared 3, the 4 would come over here, right? 4 would come over here, 3 would come over here. I would compare 4 with 2. Correct? And again, I would swap 4 with 2. Correct? So 2, 4, 2, 4, 3. So then again, I would compare 2 with 3. Again, I would swap. Fine. So what's happening? Let's just stop over here and understand what's happening. So if I put it over there, ignore this, no, as of now. Okay. Yeah. So three swapping had to be done. If okay, now I need that value, otherwise it would not be observable. So 1 was here. Fine. Again, same thing would happen for 1. You will compare 4. You would compare 3. You would compare 2, and accordingly you would swap for each one of them. So there would be again 3 swaps corresponding to 1. Correct. So 3 corresponding to 1 and 3 over here we just discussed. So 3 plus 3, 6 swaps. 6 swaps. Fine. Now if we go to selection sort, as he stated correctly, will you do all this? What will you do? You would just go over the whole 0 to n and you would find the minimum element, right? Finding minimum element does not take swapping. It only takes comparison. I told you there are only 2 fundamental operations of sorting. The first fundamental operation is comparison. The second fundamental operation is swapping. Other than these 2, in comparison based sorting, there are no other fundamental operations. So comparison we are not restricting on our system. Only swapping is what restricted. Fine. So I can do as much comparison I want. So when you find the minimum or maximum element, it will only do comparison. Once you get the minimum element, you store that in the index or any variable, and you just at the end of the day you do 1 swap corresponding to that element. So if I find over here comparing that 1 is the minimum element, I would do only 1 swap and put it like this: 1, 3, 2, 4. The next part of the list would be this part. Correct. Now again I would find only 1 minimum element, and then I would, so 2 is the minimum element, and I would swap 2 and 3 on second swap. So 2 over here, 3 over here, 4 over here. Okay, now my list would be something like this: 3 and 4. You would do only 1 comparison and see that it's not required to do any swapping, so it's already sorted. So how many swapping did you do? 2. How many swapping did you do over there? 6. Right? You got the idea, right? The difference in selection sort is you are actually finding the element on the position basis. That what is the best element to be placed in this position? What is the next element to be? What is the best element to be placed in the second position, like that? And that's why you are comparing multiple times, but we are swapping once. Fine. So that is the idea. So whenever a system is giving you restriction on number of swaps, you can use selection sort. Does that make sense? Any doubt? Okay. So, so the next thing is merge sort, right? Achha, who all have gone through the lectures for merge sort? Can you raise your hand? Only 4. Fine. So yeah, you can lower your hand. So what merge sort does is basically it breaks the it will break the array, and this is also quite important to understand. I would just briefly explain that. Sandeep, you want to ask something, or you had raised your hand earlier?
Earlier.
Okay, fine. Now, so that was insertion and selection sort. The other thing is merge sort, right? What is merge sort now? Merge sort, what it does is it breaks the list into 2 different parts, and it goes on breaking the list multiple times until and unless it gets decomposed into a single element size list, that is single elements. Fine. So let me take an example and give you how it happens. So let's say 2, 4, 1, 6, 8. Let's say 3. Fine. Please see this iteration. If you understand this, the code would also be clear. So this is my unsorted list. What will happen is this whole list would be broken up into 2 different parts at the middle. Fine. So my list 1 would be 2, 4, 1. List 2 would not list 2. I mean, the second part would be 6, 8, 3. Again, this list on the left hand side would be broken up into 2 furthermore list. So now it is an odd number of element, right? Over here, it's an odd number of element. So you can do just mid. I mean, what the way you do mid, right? The start plus end by 2. Sorry, end minus start by 2, right? Like that. You would do that. When you do divide by 2, it would be the integer division. So it would always take the up to the lesser limit. Fine. So algorithm wise, you can consider this 4 along with 2 or along with 1, doesn't matter. But basically it breaks down half. Right. So as of now, I'm considering 2 as separate and 4, 1 as separate. So other 2 lists after this iteration would be 2 and 4 and 1. Fine. So from here I had 2 lists. This list and this list. From here I had 2, 4, 1. And from this list I would have similarly 6, 8, 3. It's just breaking into halves. Now 2 is already single, so we would break 4 and 1 into halves. 4, 1. Accordingly here 8, 3. Fine. Now when we have broken up into single elements, after that you would join all the elements back. When you join back, you would see whether they are in sorted order or not. So every sorting thing would happen now. Please bear your attention here. The logic would, why we are doing this intuition would be clear. Please bear as of now. This may seem counterintuitive and make complexifying the same thing, the easy thing, but it would be quite clear after some time. So 4, 1 is there. Fine. Now when this is the leaf nodes, right? I mean, this is the last. I mean, not the leaf nodes. I mean, these are last values. 4 and 1. You have broken up into single elements. Now, when you join back, right? When you join back like this, you would see which is the sorted order. So 1 and 4, 1 is first, and then 4 must come, right? 1 and 4. So this is my first list. 2 is already a single value, so 2 will come as it is. 6 will come as it is. 8, 3 is again multiple values, so we would join that and keeping in mind the order. So here we would actually do the if operations, if and swap. Fine, 3 and 8. Now therefore we have 4 lists over here. First one is 2, then is 1, 4, then is 6, and then is 3, 8. Very important point is we are joining while doing this if and swap, that is the sorting things, sorting operations. That's why in the joining phase, in the breaking phase, we just broke it into parts, 2 halves. But when the joining phase started over here, right? When the joining phase started, these lists, these individual lists will always be in sorted order. Please keep this thing in mind. Fine. Now again, I would join these 2 and these 2 in the sorted order. So again, I have to take care of that. So I would take 1, then 2, then 4. And here it would be 3, 6, 8. Fine. And finally, I would join these 2 lists. And I'm not going in the next page, but it would give you the result 1, 2, 3, 4, 6, 8. The sorted list. The ultimate sorted list. So why we are going into so much trouble? I mean, the previous algorithms were quite easy to understand. Just put a value at its appropriate place, find the value which is minimum and put at its appropriate position. But here, why we are going into breaking things and then again joining them? While joining, I'm doing sorting. What is the requirement for all that? See, the requirement is in both the previous sorting algorithm, we got the worst case time as order of n square. We had to improve upon that. So you will go into finding why this order is n square, why it was coming as square. The basic intuition is it is coming square because in the worst case you are comparing every element of the list with all other elements, at least every element with n minus 1 element, right? Every time at that corresponding period you are comparing. That's why you are getting n square number of comparison, right? So we somehow have to join, do this sorting in a way so that if one element is lesser than another element, or if one element is greater than another element, I can guarantee I do not have to compare the some other elements. Let's say you have 5 elements, right? And you compare one element with the first element among these 5 elements. And depending upon the result you get, you can say that I do not need to do further comparisons. I can tell you confidently that my first element is greater than all the 5 of the elements or lesser than all the 5 of the elements, something like that. So that's how what I'm doing is I'm reducing the total number of comparisons. So how that can be done? That is done by using this pattern. Now you see over here what's happening. Just consider this case, when I'm joining this one, this joining, consider this joining. Fine. Arbitrarily in the worst case, if I join abruptly in the if I sort abruptly, then how many comparisons I would have required at max? I would have required to do the comparison between all the pairs of the numbers. All the pairs involved, right? Every pair possible among this group. So 2 with 1, 2 with 4, 1 with 4, correct? But when it is sorted, I do not need to do the 1 with 4 comparison because I already know 1 is lesser than 4 and I have that information at this level. So I would only do 2 with 1. And when I get 2 is greater than 1, 2 is lesser than 1 because I'm sorting in ascending order, right? If 2 is lesser than 1, I can obviously say 2 would always be lesser than 4 because this is sorted in ascending order. And that's why the first element would be the least element in its group. Least element in the sublist. Sublist is this list, this one. So if I say you this element, right, this element is lesser than the first element in the list. Now it is not lesser, but assume it is lesser. Assume this element is lesser than the first element in the list. Do I need to again compare this element with the second element in the list? I do not need, right? Because I already know this is the least one. And this element is lesser than the least one. So obviously this would be lesser than the other one. So that's how I actually reduce the total number of comparison. I do not need to compare these two pairs. Fine. So here the total comparison would be, you would do if the size is, so let's say this is an example with fixed data, right? So let's say if you are joining two sorted lists, if you are joining two sorted lists of size m comma n, so first list size is m, second list size is n. In that case, you need sorted is very important. It should be sorted, otherwise you cannot have that conclusion that if one comparison is lesser, then I may not have to do the further comparison because that is lesser than the least value. So this lesser than the least concept you would only get when it is already sorted. Fine. So you need maximum m plus n minus 1 comparisons. You do not need some order of m into n comparisons. This is the idea. This factor was actually contributing to this n square. Fine. So when you do the sorted, when you break the array and consecutively or iteratively join the broken parts in a sorted order. So in the process of joining, you would always be dealing with sorted subparts of the list or array. So when you are dealing with the sorted subparts, you can always guarantee I may not have to do all the comparison. Even a single comparison would be enough to guess that one value, if it is lesser than the least value, then I do not need the further comparison. So that's how you ignore that much time, that many iterations. Fine. In the worst case, it would take you order of m plus n minus 1 number of comparison, and in best case, you can also do away with only one comparison. Fine. So like here, it was not possible, but let's say one list is there, 1, 2, 3, 4, 5, something like this. You are joining these two. Fine. You check whether 1 is lesser than 2, you got, yeah, 1 is lesser than 2. You can directly, with only one comparison, you can directly write my array would be 1, 2, 3, 4, 5. Because this part is already sorted and 1 is lesser than the least value, which is 2. So it would always be lesser than the greater value, which is there after 2. Right. So joining sorted sublist gives you this advantage of reducing the total number of comparison. Right. See, this is the beauty. In the previous example, we discussed that if there is a swapping constraint, then you take selection sort. Correct. Now here it is a lesser number of comparison is required. So merge sort is much better in terms of comparison. Selection sort, all the worst case is order of n square, but performance wise selection sort takes lesser swapping time. So if your system takes more swapping time, selection sort takes lesser number of swaps. So if your system takes a lot of time while for doing swapping, selection sort can be a good approximation, right? But merge sort is always a better approximation because it takes a lesser time, because it does lesser number of comparisons. And also, if you think about it, irrespective of whether you give a sorted array in any way, ascending, descending, same value, different value, random, since it is breaking down up to the bottom level, right? See, up to the single element level, right? So it doesn't matter what is the order that you have given. Every time it would join it in the proper order that it wants to, ascending or descending, right? That's why I said while discussing the average time complexity, irrespective of the property of the input that you give to merge sort, it will always give you n log n complexity. So this is merge sort is actually theta of n log n. You got the idea why it is so? Because you are breaking it down to the level of single element over here. So it doesn't matter.
Hello.
Yeah.
Hello. So supposedly instead of 2 there is 5. Then we have to compare it with the first element in the right side, that is 1. And number of comparisons
can you tell over here, right? 5.
Yes.
Okay. Then
I have to compare it 2 times, no, with 1 and 4.
Yeah. 5, 1 is there, 4 is there.
And 4 is there.
Yeah, so I told you
here number of comparisons.
5 would be compared with 1, 5 would be compared with 4. Correct. So 2 comparisons. Right? Comparisons. What did we discuss? The size if it is m into n. Worst case number of comparison was equal to m plus n minus 1. What is m here? 1. What is n here? 2. What is m plus n minus 1?
2. So could you please tell me why you have written minus 1? M plus n I got it, but why it's minus 1?
Yeah. So if you have, say, let's say 2, I'm not taking into consideration of the order. Okay, wait, just a second. 1, 2, 3, 4, 5, 6. These 2 are both sorted sublist. I want to join them. Fine. Sorted is very important. It should be sorted. So why it is so? See, why it is n minus 1. So if you do check with 1 and 4, right? Check 1 with 4. Okay, no, if I do that, then it would always be the best case. So this is actually the best case, you can see. If I do 1 with 4, I can guarantee that 1 is lesser.
Yes, sir. Yes.
So it's the best case. You will already, so this example would not solve it. Let's take some, let's swap it. 4, 5, 6, and 1. 4, 5, 1, 2. Yeah, so this is fine. So now you compare 4 with 1, right? 4 and 1. You see that 4 is not lesser than 1. Correct? 1 is lesser. You see that 1 is lesser. Fine. So you can keep the lesser value here, 1. Okay. But since 4 is not lesser, I mean, not the least value, 1 is the least value, that is fine. But 4 can also be greater than 2. I mean, it's there is no guarantee, right? I am saying that 4 is not lesser than 1. If 4 is not lesser than 1, I don't know whether 4 is lesser, I mean, greater than the value which is coming after 1. If it would have been lesser, then I can guarantee that all values subsequent to 1, from them 4 will also be lesser, because this is ascending order. But I cannot guarantee it now. So 4 would also be compared with 2 in this scenario. Right? So, yeah, so you are comparing that and then comparing 4 with 2 also in that case. So first one would be placed. This is iteration number 1. Second iteration would be with 4 with 2. Fine. One is already placed. So this is my second iteration for 2. First iteration, second iteration. 2 is also placed. Fine. Now see. So 2 is also placed. Now what I am left over with? 4 and 5. Correct? Got the point? Any doubt up to this point? 4 is the least value among 5. 4, 1 compared, 1 is lesser, placed 1. 4 and 2 compared, 2 is lesser, placed 2. Fine. Now what I am left with? 4 and 5. Do I need to compare 4 and 5?
Oh, no, sir. Oh, yeah.
It's sorted, right?
Yeah.
So it's m plus n minus 1.
Yeah. Okay, sir. Thank you.
Fine. So this is the advantage. So I can only use this fact that I do not need to compare 4 and 5 because of the reason we are comparing all the sublist in their sorted form. If it's not sorted, I cannot say that 4 is lesser than 5. I have to check that. But since it is sorted, I can say, okay, I have got the whole list and it is sorted. So anyway, it should be something, I can directly place it the way it is. Fine. So it is m plus n minus 1. Now you can relate. 2 plus 2 minus 1 would be the maximum number of iteration, which is 3, right? If you see here, we did only 3 comparison. 4 with 1, 4 with 2. Oh, we even did not need that. Only 2 comparison was enough. Fine. At worst case, you would need 3 comparison. And in the best case, you can also go with 1 comparison. No, 2 comparison. Yeah, best case also you would need 2 comparison over it.
So, yeah, 4 with 1 and 4 with 2.
Huh. So that is the advantage of merge sort. It gives you n log n average time complexity. The reason for that is it breaks down the array to the very basic level of single elements, and it joins all the single element one by one, considering the sortedness among the sublist. And because of this feature, it totally erases the property of the input that you have given, whether it is sorted in reversed order, whether it is sorted in the order that your algorithm is going to do, whether it is repeated element, doesn't matter. I am breaking it down to the bottom level and then I am joining it according to myself. So that's why the property or that feature we discussed now, the property of input may change your time complexity. That does not happen in merge sort, and therefore merge sort gives you a n log n time, theta of n log n time. Fine. Yeah. So 2 points. Selection sort is efficient in terms of swapping. Merge sort is quite efficient in terms of comparisons, number of comparison, and also merge sort gives you a worst case and best case both as n log n. That's why merge sort is quite useful. Fine. Now, since most of you have not done the merge sort problem, I mean, not learned that code. So otherwise, for homework, I'm giving you one problem, not homework. Just you can see that when you use merge sort, you have to copy the element in a temporary array every time. Right? What I mean is, we did over here, right? 1, 2, 3, 4. This 4, 5, and 1, 2. So we were joining it. So when you join this, right, you cannot do it on the same array. So you need a temporary location to put 1 first, then 2 first, depending upon the comparison, then 4 and 5. Once you have obtained the full sublist, then you can copy it into the primary array over here. Right? And again, you can iteratively go on recursively do that. But you need a temp array, an array or list, whatever you say, a temporary location to do the joinings. But there is a way out without using this extra temporary location of doing merge sort, which we call in place merge sort. And this is very interesting. Okay, and this actually uses a very simple trick of maths, not any trick or any idea of algorithm, but a simple trick of maths. So I'm just accepting that you would be able to get this idea directly over the web, but I'm requesting you don't see. Try to think in terms, try to think of it. At first, go through the code of merge sort, see that there is an extra space requirement, and then try to think, how can I, without using this extra space, how can I do the merge sort? Okay, and so those who would think honestly, I'm just giving you a hint on in which way how to think about that. So you would not be required to modify the element of the list if you use some operations like modulus, division, and multiplication on those elements. Right? Another hint is, so this is hint 1. The second hint is you have to do something with respect to finding the max value within the array. Some value which is greater than the max value, that is better to say. Some value which is greater than the max value of elements in the array. In the list, sorry. Fine. So you need to find some value which is greater than all the elements in the list, and you need to use some operations called like modulus, division, and multiplication. So this is a hint, right? And what you would do is basically you would somehow modify the contents of the array. Let's say AI is one value, right? So you in merge sort, what you do, if AI is greater than AJ, right, then you would do something, right? So so in this place, while without copying the element which is lesser into a temporary location, what you can do is you can change the element AJ itself to something else, which is basically a function of these symbols and the max value. Right? Max something. So this is the hint. What to do, how to do, that you have to think about without using any extra space. You do not need any extra space. One important point is you may or may not require all of this symbol and values together. You may need it separately, you may need it together, whatever it is. You have to think about it, but it would be of some form like this. Right? So that is in place merge sort. You would not need the extra space. So merge sort is done. It's quite 10:24 today. So only one thing is left, that is binary search, right? Binary search we would discuss maybe in the live coding session. Before starting that, we would discuss. Fine. Linear search is quite simple. You have already done that as a part of your insertion sort. What you do is just go on linearly checking all the elements. So that is fine. Binary search, there are some interesting problems. We would discuss that on the next session before the live coding starts. Fine. Okay. Any doubt in this part? Any merge sort? Any doubt? Why it is advantageous? The difference when to use selection sort, when to use merge sort, when to use insertion sort. A basic idea.
Yes, sir. Yes.
Okay. Fine. Thanks a lot, all of you.
Thank you. Thanks a lot.
Yeah.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.